So good morning, everyone. So we continue with the revision of electrostatics. And electrostatics is some part of electrostatics, which is electrostatic force, field, potential energy. They are very similar to gravitation. So what you have done in gravitation, same thing is applicable. And only one area it differs significantly from gravitation is application of Gauss law. And the Gauss law part and the questions related to Gauss law. And in short, this is how we express this Gauss law. Electric field flux through a closed surface is equal to charge enclosed by epsilon naught. And there are typically three cases Gauss law is very useful. And whenever we apply Gauss law, we have to have a fair idea about how the field lines are. So typically it is used in case of symmetry. And three kinds of symmetries are possible. What are three possible symmetries we very often use? One is spherical symmetry. So spherical symmetry, what is we make use of? Spherical symmetry means if charge distribution is spherically symmetric. Simplest case we can think of, if charge is distributed over a surface of spherical shell, the field lines, if charge is positive, fields are radial direction. Field is in the radial direction and there's no field inside. So that is one part here. So field is radial. This is one kind of symmetry. And this is also various questions have come. Spherical symmetry. So in case of spherical symmetry, to take advantage of spherical symmetry, we typically choose a concentric Gaussian surface. We take a concentric spherical shell. And when we take a concentric spherical shell, important point is every part of the Gaussian surface, whatever small area we take here, field is perpendicular to the Gaussian surface. The angle between field and area vector everywhere on the surface is equal to 0 degree. So dot product thus becomes easy. So one is spherical symmetry, and this is something we will go through some. Second type of symmetry is cylindrical symmetry. What is cylindrical symmetry? There's two ways we can understand them. One is a long thin wire. Long thin wire also is a long cylinder of very small radius. Or it could be a long cylinder also. If you look from the top, long cylinder cross section. So what is important in this case? Whenever we have a cylindrical symmetry, the field lines will, what is the nature of field lines? If I look at the wire from the top, if it is a wire, positive charge, field lines are radially outwards from the axis of the cylinder. So here we take a Gaussian surface, which is of form of a cylinder, which could be something line wire, it could be solid cylinder, it could be hollow cylinder also, or it could be a combination of hollow cylinder and solid core. All such cases is cylindrical symmetry, and we take a Gaussian surface, which is concentric cylinder of some finite length. This way, to have symmetry, this has to be long one. And third kind of symmetry is planar symmetry. So what is planar symmetry? If you have something like a sheet of paper, a plane object, and there's a charge which is uniformly distributed on the sheet. If charge is uniformly distributed, this is something we're looking at 3 dimension. If we take a side view, this is something we see 1 dimension, but plane sheet extend perpendicular to the sheet here, perpendicular figure of drawing here. If charge is negative, the field lines are perpendicular to the surface except for the edge region. So we only focus on the central region. So here field is perpendicular to the surface here. And in this case also, we can take a Gaussian surface such that we can take a Gaussian surface like a cylinder also. And axis of the cylinder is perpendicular to the surface here. So these are 3-4 cases we make use of, and the certain formula also. Okay, so let's go through some questions, and quite a few questions have come on this and others as well. So something like this is given. Let's understand this part. Spherical symmetrical charge distribution is given, and charge distribution is given like this. So density is rho naught 1 minus small r by capital R. So when r is equal to 0, it is rho naught. At the surface, volumetric charge density becomes 0. It's a function of distance from the center. It doesn't depend on the orientation. That's why it is a spherically symmetrical charge distribution. So what we need to find, and there's no charge after, so something like this. If this is center here, near the center charge density is maximum, which is rho naught. As we keep going over the center, it drops to 0 and 0 after r naught. At distance r from the center of the charge distribution, what is the field? So if I need to find a field in such kind of charge distribution at a point P, which is a distance of small r being less than capital R, is interior point. So if we have to find a field because of spherical charge distribution, we'll take a Gaussian surface running through P concentric spherical shell. So this will become my Gaussian surface, and thus we apply. And when is Gaussian surface here? So this part is very easy to write. Every small area field will be perpendicular. So this term will be equal to everywhere field magnitude is same. So it will become E into surface area. So this term very easily comes equal to something like this. Gaussian surface, field at a distance r, surface area is 4 pi r square, is equal to total charge enclosed. So when we look at this kind of charge distribution, see, we can think of several spherical shell, and the part of the sphere which is outside point P, or part of the sphere which has a radius greater than small r, this part will not contribute to any field at point P. So we ignore the part which is outside. We just need to calculate what is the total charge contained. Charge enclosed is what? If I have to mark what is the charge enclosed, this is the volume which I need to take. So I have to calculate the total charge enclosed here. And since the density is not constant, I cannot write density into volume. Density is a function of R. So such cases, this sphere also, we need to assume several concentric spherical shell, and we need to calculate charge on a random shell and add it up. So what is charge contained within a radial distance R is equal to sum of charge on all spherical shell and radius ranging from 0 to R. And then this is a function of R. So here also rest is very simple integration. So we find from here, if we integrate, we get a term QR. QR indicates charge contained within a distance R. And we substitute here, we find the value of electric field. And these are simple definite integration. All of you can easily do that. Similar question, and this has come in different forms. So just let's look at this. All require very similar approach. Only thing what happens, the integration part is changing. So again, let's look at this. Charge is distributed within a sphere of radius r, and charge density is something like this. It's a negative exponential function. And I don't know how many of you, if you understand what is the shape of negative exponential function. We have come across negative exponential function number of times, and we come in case of radioactive decay and other cases also we come across. So negative exponential function is something like this. Its charge distribution is something like this. It's going like. So thus, as we keep going away, the density is decreasing. So what we need to find, if Q is the total charge, then find the radius R here. Okay, distributed over a sphere of radius r. So we need to find what is the charge contained within a distance r. That's what we need to find. And how do we find total charge here? Again, density is not same. It's very similar to previous question. I need to find Q for r equal to capital R. How would I find? Again, sum of charges on spherical shells. And so we take a random shell. So again, similar to previous question. Density at a distance r into volume of spherical shell. This is surface area into dr. That density, and this becomes volume. This is charge contained in spherical shell of radius r, thickness dr. If I integrate from 0 to r, I get the total charge. And the total charge is equal to Q. Q is the total charge of this distribution. Sorry, in this case, total charge is Q. So total charge we have to include, I have to include 0 to infinity. So total charge Q will be something like this. We integrate from 0 to infinity, 4 pi r square. And whatever density is given, we substitute here. It becomes a by r square, e divided minus 2r by a into dr. That's the expression. So this gets cancelled. Of course, 4 pi a is a common term here. It's a simple integration of this term. it is equal to e raised to power minus 2r by a with appropriate limits. So this becomes equal to 4 pi a. And all of you, I think, easy to integrate exponential. And it will become equal to e raised to power minus 2r by a divided by, yes, Group.
So the limits are 0 to r, right? Because they give sphere of radius r, right?
Then the charge is, I think I have some mistyped here. The total charge Q you need to calculate. What is the total charge? Since the exponential one, the charge distribution will continue up to infinity. Okay, so I think maybe some small error in typing the question, but this question was total charge. Sorry, then, okay. Yeah, something, I think there's some mistype here, but it's a total charge, very simple integration. So we can look at that. I can get that answer also. So something is missed here. Okay. So again, some less question. So basically, all are integration. All are. If you do integration, you can easily get your answer. Something like this. This also kind of question common. This is cylindrical symmetry. A long, infinite long cylinder, radius r, has uniform charge density rho. It has a spherical cavity of radius r by 2. This is spherical cavity here. And we need to find field at a point P, which is at a distance of 2r. So first, if this question, if we need to find field at a point distance r from the center, in case of cylindrical charge distribution, what kind of Gaussian surface we need to take? So in this case, question can, as I said, cylindrical symmetry, line charge. It could be hollow cylinder, it could be thin hollow cylinder, or it could be a combination of those. So if we need to find, in here in this question it is not so, but if we have to find E at a distance r, r less than capital R. Again, we'll take a, which kind of a Gaussian surface? We take a Gaussian surface, which is which must pass through the point P, where we need to calculate the field, and it has to be a kind of cylinder. Say a cylinder of length L. And in this case, Gaussian surface, top surface, bottom surface, bottom surface, the field lines are perpendicular to the axis. And hence no flux will pass through top surface and bottom surface. Here the flux will be equal to lateral curved surface of the cylinder into the field strength. So it will be ER into lateral surface area perimeter 2 pi R into L. So that would be the flux field into area. And that has to be equal to charge enclosed here. If it is uniform charge distribution, and if it is not uniform also, we could have written like this. Yeah, if it is not uniform distribution, since it is uniform, charge enclosed will be equal to, let's write the charge enclosed in case of a cylinder one. Charge enclosed will be density into volume enclosed by Gaussian surface. So volume enclosed is equal to volume of cylinder and density is rho. So very simple, and volume we write as pi r square into L divided by epsilon naught. So we can find out field if it is inside. Since when it is outside, another point we notice, if the point P is outside, this cylinder behaves like a line charge, very similar to a way spherical charge distribution behaves as if entire charge is placed at the center. Similar logic, if you take the Gaussian surface, it doesn't matter where within the Gaussian surface the charge is placed. So here, whenever we have to find field at a point outside because of cylindrically symmetrical charge distribution, I can still use the formula of line charge. And line charge formula like this. What is the line charge formula? Line charge formula is lambda by 2 pi epsilon naught r, or you can also write as 2k lambda by r. That's the field. And what would be charge per unit length here? The lambda will be equal to density into area per unit length. So lambda can be written as density into pi r square. So I can find out field also. So this question is fairly simple. The field at point P will be equal to this lambda term. And so field at point P due to, so we use principle of superposition due to solid cylinder minus the cavity. The field due to solid cylinder will be equal to this formula. Lambda will be equal to rho into pi r square divided by 2 pi epsilon naught into distance is 2r. Thus a field created by a solid cylinder, and then we'll subtract field created by the cavity. Field cavity, this is spherical charge. So just the density into volume, kq by r square. And we subtract this field here, we get such cases here. So this also should be able to easily solve. Okay, one more question, something of thin disk. So what was given here, this is 2015 question. And as I mentioned here, the 2015, 16, 17, some questions were a little more difficult than kind of questions we come across in the recent past. A thin disk of radius b is equal to 2a. So this, if you look from the top, it's a solid disk from where part a concentric disk has been cut and removed. It's like a annular disk. Outer radius is 2a. Inner radius which has been cut and removed is radius a. It carries a uniform surface charge sigma on the surface. So this is where the surface charge is. We need to find electric field at a height h from its center, perpendicular to its plane. And so how do we calculate field here? So the two ways, either if you remember the formula for circular disk here. Formula for circular disk at a height z is something like this. The field at a height z is equal to C. Circular disk also in a way similar to surface charge. So if you want to remind the formula, it's very similar to this one. But if it is circular disk, its area is not infinite. Hence we subtract something. What we subtract here, it is equal to minus z and divide by inclined distance. What is inclined distance? R square plus z square. That's the formula, and I just see that the logic also you understand. So if it is height h here, h, and what is in the denominator? This inclined height. So this number will always be less than 1. And when z is much less than r here, when z is much less than r, this term becomes close to 0, and you get a formula for infinite surface charge. Even if we do not remember this formula, still we could have solved. It is like a circular disk with a central cavity here. We can treat that is a several concentric circular ring. So I can use circular ring formula to calculate for this also. So what is several concentric ring? We'll feel all circular ring, distance h is constant. So I can use my formula for circular ring. The formula is k times the charge. So charge here will be on a circular ring, charge will be equal to charge per unit area into area. So circular ring 2 pi r into di becomes area here. This is distance term on the axis x, and this is r square plus x square 3 by 2. That formula here. And this also, the limit will be from a to 2a. And since all of you have done a lot of definite integration, you clearly notice here this r term here. So I can substitute, we can easily substitute this term as a t or t square. Anyway, it is okay. R square plus h square. If I substitute a t square, and after substitution, I put the limits back here, I can easily integrate and solve here. So this question also, I suggest all of you, this is more of a practice of definite integration also. All of you should try and solve. H is much less than a. So we'll use the approximation later on. In the final result, we use this approximation. So this is something, is an example of finding limits also. Integration with limits. And this also is a good question. And again, you notice spherical symmetry here. And so the a region between two concentric spheres of radius A and B. So there are two concentric spheres, A radius, B radius, has volume charge density rho A by R. So where is the charge here? In between the two. The shaded part contains charge, and this cavity, and there's a point charge Q placed at the center of cavity. So between 0 to A, except for this charge, there's no other charge here. What is asking here, if the charge here is function of, basically what's saying, the charge density in this region is a function of distance from the center, is A by R. So as the distance increasing, the volumetric charge density is decreasing here. So we need to find what is the value of A such that electric field in the region between the sphere is constant. So basically E for ER, for which region? For R varying from A to B is constant. So what has the value of A? So this also approach is very simple. We'll find value of field at a distance r here. And we see what is the condition we need to apply to make it independent of r. That's constant mean. So here, what is the expression we write here? Let's first find out, sorry. We find out field at a distance r here. Finding field at r is simple enough. Field at a distance r in that region here will be equal to due to point charge kq by r square. That part is simple. And it also because of charge distribution here. And what would be, how do we find field due to this volumetric charge distribution? By using Gauss law. If I take a Gaussian surface, and since the field is radial, E into R into, where we have done this earlier, 4 pi r square, is equal to charge enclosed between 0 to R. So whenever you have something like this, we need to find this term QR here. And what is the QR? QR is the total charge enclosed between distance 0 to r, excluding the point charge. Point charge we already taken here. And this term is always equal to rho r into 4 pi r square dr. And what is the limit we'll take here? Since there's no charge between 0 to a, the lower limit will be a, upper limit will be r. So this we calculate here, charge enclosed within radius r. We substitute it here. We find the total value of field, which is sum of the two, and see that what makes it 0. So all of you try and solve this question fairly easy afterwards. Not a difficult question. And you can find, so basically the coefficient of r term has to be 0. Then only it becomes equal to, it becomes independent of r. Some questions on surface charge distribution. See, what is surface charge? See, before I do this question, one more point you need to keep in mind. See, if there are two sheets, like two sheets of paper, and the sheets of paper are perpendicular to the plane of figure here. These are field sheets are extending into the plane of paper. And this sheet has charge density sigma, and this also has a sigma. So if two charge sheets are placed parallel to each other, we know because of, and in this case, we assume sheet to be very large in size. So large in size compared to the distance we measure here. If they are like infinite sheet charge, equal sheet charge, the field lines are perpendicular to the sheet. That's the first thing we need to understand here. And hence field is independent. And if field lines are parallel, it means it's a uniform field. So sheet charge creates a uniform field on either side. And field strength is, we can easily derive that equation also. This is equal to sigma by 2 epsilon naught. So this is the field created by left sheet. Similarly, if I draw the field created by the right sheet also, if both are same sign, this also will create field which is going away from the sheet. So this also will have field like this. And what is the important point we notice here? See, in the region, this part also, both fields are adding up. This part also, both fields are in the same direction, adds up. In between, the fields cancel out. So whenever equal charges are placed on either side, field in the central region becomes 0. Whereas if the charges are opposite, they tend to add up. So that's the point we need to keep in mind. Suppose rather than having two sheets, if I had multiple sheets also, but as long as charge distribution is symmetrical on either side of this plane here, if charge distribution is not two sheets, if there are 20 sheets this side, 20 sheets this side, its distance is immaterial because here field does not depend on the distance. As long as for any sheet on left hand side, there's a corresponding sheet charge on the right hand side, which has same charge density, the net charge created is 0. Let's use this one to solve this question. And this also is important. I think this step, perhaps students, most of you may find this one little more challenging. So try and understand this part. So we'll do a couple of questions based on this. So a non-conducting sheet of large surface area. So it's like a book. Just imagine what is this one? It's like a book, and book has several pages. Each page is like a charge here. Okay. So if a book has 100 pages here, and it has certain thickness. So we can think of charge distribution as 100 pages, and it has certain thickness. I can say its thickness is T. And each page has equal charge. It means charge density is uniform. A non-conducting sheet of large surface area. Why non-conducting? Had it been conductor, charge would have gone to the surface. Only non-conductor, we can have any kind of charge distribution possible here. And thickness is d, and uniform distribution density is rho. So overall entire volume of this volume, this is the charge per unit volume here. Find the electric field at a point inside the plate at a distance t from the central plane. So what I've shown here, the shaded part is the central plane. So if this book has 100 pages, it means 50 pages are on this side, 50 pages are on this side. And since both have same symmetrical charge distribution, same charge density, equal charge on the right side, equal charge on the right hand side. So on the central plane, because of symmetry, field will be zero. That's first point we need to understand. So this is three-dimensional view. If I take a side view, so if I take what is the plane here? When we talk about sheet, it is surface, and surface normal to the surface is along x-axis. This surface here, all sheets are in YZ plane or parallel to YZ plane. So understand the orientation of sheet. So whenever sheet charge is there, field is perpendicular. So here also, every single sheet will have field which is perpendicular to the sheet. Hence, all sheet to put together also will have fields like this. So direction of field lines will be like this, but it is not like this, because wherever charge is there, field lines can start. So some field lines starting from the first sheet, second sheet. So as a field is not uniform, but everywhere field lines is perpendicular to the area. That part we need to understand here. So that's how the fields are. And if I take origin at the midpoint here, so right on, if origin is taken at the mid thickness here, total thickness is how much? Okay, so the total thickness is d. So if I take midpoint here, at all points at plane, does it make sense? If plane x is equal to 0, field is 0. At plane x is equal to 0, field is 0. And everywhere, any point, if we calculate field, the field on the right hand side for the region. So first of all, I hope you understand. First of all, what is the sheet charge here? Sheet charge, what is the orientation? Sheet charge is such that area vector is along I cap, or you can take a minus I cap, because this in this case we get. So that's a sheet charge. Hence, what we understand here, hence field also will be either along I cap or minus I cap. So for region or for surface x is equal to 0, field is 0, that also we should understand here. And field for region x greater than 0, field will be along I cap, and field for region x less than 0 will be equal to minus I cap, direction. So this will be the direction of field. So that's what you should understand here. And this is the 0. Now we need to find field at which plane? We need to find field in a plane where x is equal to what? We need to find field at x equal to t. So if I have to find field at x is equal to t, I have to take a Gaussian surface. What is the Gaussian surface here taken? We have taken a Gaussian surface which is cuboid. And cuboid, so cuboid has surfaces. See, there are two surfaces parallel to YZ plane. This surface also is parallel to YZ plane. This real surface also is parallel to YZ plane. This surface is at x is equal to 0, and this surface is at x is equal to t. So whichever point I have to calculate field, point P lies on the right surface of the cuboid. In this cuboid, I apply the Gauss law here. How do we apply Gauss law here? We calculate what is the flux. So when we calculate flux, it has 6 surfaces. Out of 6 surfaces, 4 surfaces are normal is perpendicular to I cap direction. So this also, all 4 surfaces, area vector is perpendicular to field vector, hence flux will be 0. So flux is non-zero only for 2 surfaces. Which 2 surfaces? The surfaces, one is the left surface. The area vector for the left surface will be in this direction. Area vector for the right surface will be in this direction. Thus n cap direction for area. This surface, the flux will be 0 because I have taken this area at x is equal to 0. Because symmetry here, field is 0. So this surface also has no flux. Flux is only through this surface. That's all. And since this surface is parallel to YZ plane, field everywhere on the surface is constant. So let me write what is the total flux through this Gaussian surface. What is the flux through this Gaussian surface? Flux to Gaussian surface is equal to field into area. And since they are along the same direction, cos theta is equal to 1. So this term here for this Gaussian surface, E dot dA, will be equal to field at a distance t into area. So let's say the area of this cube is each surface is L, or I can say if the side of the cube is L, area is L square, is equal to charge enclosed. How much is charge contained? Volume of the cube into density is a uniform density. So this into volume is equal to L cube divided by epsilon naught. That's a field here. And sorry, not L cube, sorry, 1 minute. Area, this side is L, but this thickness is T here. So it will be L square into T. L square into T. So what is field equal to? Field is equal to rho into T by epsilon naught. Okay. Vikram, have you followed this?
Yes, sir.
And this is, I have taken a little more time so that you understand whenever we come across sheet kind of charge, how do you handle such things? Okay. So something like this, and you can solve. Okay, continue with some more questions. XYZ space has infinite surface charge having charge density sigma, and this surface charge is placed on YZ plane. So moment we say this surface charge is placed on YZ plane, so it is something like this is placed on YZ plane. So what is the field it will create? Suppose the question was write an expression for field due to this charge here. So sheet charge will always create a field which is perpendicular to or to surface here. It is YZ plane, so it will create field only along the I cap direction or minus I cap direction. If charge density is positive for region x greater than 0, the field will be equal, field will be in this direction, field will be equal to sigma by 2 epsilon naught and I cap direction. And for other side of the field, so if this is how the sheet is, and if charge density is sigma, this is how the field is. So we know how to write that one. For x less than 0, field will be equal to same thing, magnitude, but in the opposite direction. This is how the field is, right? But this is not the only charge. We can always use superposition. So we can calculate the field due to surface charge first. And there's a negative charge of particle minus q placed at A00. So along the x-axis, there's another charge particle also placed here. Okay. The variation of electric field on x-axis, it will not vary. At the field will only depend. Okay. So on x-axis, this is how the field is. This is how the variation of field is given. Based on this, so where is charge q placed? Charge q is placed at which point? Charge q is placed at this point. This is charge q here, minus q. Based on this, we need to find a relationship between sigma and q. How do I find the relationship between q and sigma? We need one equation. So can anyone spot what is the way to find relationship between field created by sheet charge and what is shown here is resultant of field created by sheet charge and point charge on which axis? Only on the x-axis. So important point what we notice here, it shows a particular point where field is 0. We can spot the null point here. Which point the field becomes 0? If we spot, we can write a condition for this and then becomes easy. So this question from the graph, only thing we need to spot is field at x is equal to 2a is 0. So I'll write field due to sigma. So field at x is equal to 2a. Due to sheet charge, we have already written here. Due to sheet charge, it is equal to sigma by 2 epsilon naught. I cap positive. And what will the field due to minus q charge? Minus q charge, this charge is minus q. So point is coming on the right hand side. field will be towards left. That's why it is becoming 0. So I'll write equal to, direction is minus I cap. I'll write the magnitude now. We understood the direction. Magnitude will be equal to 1 by 4 pi epsilon naught into the charge divided by square of the distance of the point from the charge. The distance is equal to A divided by A square. Sum of these two are 0. One is plus I cap, second my cap. So I equate the magnitudes, I get my answer. This magnitude equated to this, I get my answer here. Yes, Alan?
Sir, how do we know where the sheet is placed?
It's written, placed on clearly written.
We gave XY, I mean YZ plane, right?
YZ plane. If a YZ plane, you understand, it's not parallel to YZ plane. You understand difference between the two words? If it was
like
mentioned parallel to YZ plane, then it becomes more tricky. No, so it is YZ plane. Okay, and that question also is actual question. So that's how it has come, and you should know how to. So any doubt also we should not have, and that's the only way you could have solved. Now coming to next question is electric field vector is given like this. Okay, that's how electric field vector is, and we need to calculate flux through a cube bounded by the surface here. So if it is given also, first of all, I think you have done enough mathematics. You can easily visualize what this is. So the surfaces are x is equal to L, next surface is x equal to 2L. And so it becomes like this is a cuboid here. Electrical field is like this. We need to calculate flux through this surface, and this forms a closed surface. And any closed surface, there's a definite area vector direction. The left surface area vector direction will be minus I cap, and right surface area vector direction will be equal to plus I cap. Okay, so so area vector direction is outward normal as positive. So we need to calculate flux. So fairly simple. So first thing we notice, how is the field direction? And just understand here. If I understand field here, important point is it's a non-uniform field. It is varying with x, so it is a non-uniform field. So non-uniform field, if field was uniform, its flux through any closed surface would have been 0. Since it is non-uniform field, it means there's some charge present which is changing the field here, non-uniform field. Second important point, what I understand here, field direction, though it is non-uniform, its direction is only along I cap. If direction is only along I cap, all area vectors which are perpendicular to I cap direction will not have any flux. So out of 6 surfaces, 4 surfaces will have 0 flux. Non-zero flux will be only due to for this surface and this surface. These are the 2 surfaces which will have non-zero flux. And I will take the dot product of field. So here, everywhere the field is this surface, everywhere x is constant. And since field is a function of x, all over the surface, the field is constant in magnitude as well as direction. And the direction of field is something like this. Direction of field is I cap. Area vector is minus I cap. Hence, the flux will be equal to minus E into area. So this area left surface, what is the flux through left surface? If I write E dot I, very simple, flux angle between them is 180. Hence, it becomes equal to, what is E here? E will be equal to magnitude of E, A, and X is equal to root L into area. Area is L square. That is the flux in, and it is negative. This is through the left surface, flux through left surface. And what would be the flux through right surface? Again, the direction of field is not changing. If I mark how the field is all over the surface, everywhere field is on the surface, entire surface, x is constant. Field is a function of x alone. If x is constant, field is constant everywhere on the surface. So no need for integration. Straight away, E into area vector, and angle between them is 0, cos theta is equal to 1. So again, E at a distance 2L here. Since here at this point, x is equal to 2L, hence the field also will be equal to A into root 2L into L square. This is positive. So what is the net flux will be equal to? Net flux will be equal to AL square root 2L minus AL square root L. Okay. So that's a flux. And so with this, how we calculate charge enclosed. And this is the question, which is, they say, what is the flux bounded by the surface? A very small extension of the question will be, what is small extension? Find the charge contained within the cube. Find charge contained within the cube. Yes, anybody has a question?
Sir?
Yes.
So it's possible that the flux on the other four faces is non-zero due to the charge present, but we're not concerned with that, right?
No. Then you tell me again.
Like there's a charge present inside the cube for sure, right, sir?
Yes.
So there might be flux through the other four surfaces.
No. This can be answered with what we have done 10 minutes back. What kind of charge distribution can create a field which is only towards x direction?
Okay, so it's a surface charge.
Yes. So that is surface charge. It won't have field. So that's the next part. If I can calculate, this is charge contained, but it's a part of long sheet charge, and it will not have any component along any other direction. Valid question, but this is something I think you have understood. This part doubt we should not have. So if we have to find charge contained here, charge contained also easy. We have calculated flux through a Gaussian surface, and this flux I equate to charge enclosed by epsilon naught. So I multiply the net flux by epsilon naught, I get the charge enclosed. So this also I can find. And third part, little more tricky would be if I have to find one more question. What is the charge density as a function of x? Can we find charge density also? So that's the part, third part. I think I have some other question I'll do again. So if I have to find charge density, this is total charge contained in entire volume. I want what is the charge per unit volume. How would I calculate? Suppose I want to find out what is the charge density at x is equal to 2L. Can someone think of what is the way to find charge density, volumetric charge density x is equal to 2L? In that case, if I have to find x is equal to 2L, I will take a Gaussian surface, which is not a cube. I will take a Gaussian surface, which is of length equal to dx. So I will take a Gaussian surface. One face is at a distance of 2L. Other face is at a distance of 2L plus dx. And then again, I can find what is the total charge contained within this thin slice. So I will take a kind of slice kind of thing. And once I have this, I think I have one more question. I'll do something later, something similar. So this could also be a question. Find charge density. It's a reverse of what we had done some time back. Okay, so I think this question, similar question is there later on also. When we do that, I think we'll get an understanding of this. Okay, now moving on to electric field. And electric field and potential differences are related. What are minimum things we should know? Delta V, change in potential is equal to negative of work done by electric field. Okay, so we assume this electric field, whenever we define potential, this field is due to system of charge, and we assume this is to be fixed. So the concept of potential makes sense only for fixed charge system. And if the field is uniform here, then we can write not only dV, the delta V also, the potential difference between 2 points, which are not necessarily very close to each other, it becomes this term here. And if it is not uniform, then we need to do for integration. If I have to find potential difference between A and B, so basically if B becomes the starting point, so as we move from B to A, what is the change in potential as we move from B to A? That's what this expression means. Change in potential as we move from B to A, it is equal to work done from B to A, negative of that. So that's the three things we should understand. And from here, we also get a relationship. Even we can write what is Ex also. I think written earlier in case of gravitation. Ex is nothing but d, partial derivative of potential with respect to x direction. So these are things we should know about relationship between field, potential, and potential difference. So let's see what is given here. A uniform electric field. So moment you see uniform electric field, I don't have to go for integration. This is adequate. It's directed 30 degrees with the positive x-axis shown. Find the potential difference VBA. So whenever VBA is mentioned, VB minus VA. So we need to find, as if we are moving from what to point. So if at all we have to look for displacement, we are looking at this displacement. Delta R is this. Well, what is the direction of delta R here? If I have to write delta R, which term will come first? VB minus VA. This is my displacement. How would I move? This is the way to displacement has to take place. So this is your delta R vector here. This is delta R. So one way of solving this question, I can do more in form of vector form. So what we do in terms of dot product. So I am going, one way of solving will be, I'll solve using delta V is equal to minus E dot delta R. Let me write both terms in the unit vector form. E magnitude is given 100. It is inclined 30 degree with the positive x-axis. The unit vector will be cos theta I cap, or we can put the value, and sin theta j cap. That is, this unit vector is valid for all theta, where theta is counterclockwise measured from positive x-axis. I substitute, I get value of E. How do I get delta R? Delta R will be equal to RB minus RA. RB is equal to what? RB OB is 4M. So RB is equal to 4J cap, and RA is equal to minus 2I cap. Then I take a dot product, I find this one. So fairly easy, we can I can get this expression. Okay, next question. And this question I think I had done earlier also, but this question people easily get confused. I'm quickly at this time I'll do a little faster. This also past question and very good question. There's a uniform electrostatic field in a region. Okay, the field is not changing. It means there's no charge contained in this region. Potential at various points in a small sphere centered at P in the region. So they're imagining a sphere which is centered at P, a small sphere. It is found, potential is found to vary within maximum is 589.0. Sorry, this minimum to maximum, this is the limit at which potential is varying. What is the potential at a point on the sphere whose radius vector makes an angle of 60 degrees with the direction of field? Okay, so first understanding, and since directions are involved, what we do, you always have a, whenever it is not mentioned, we can always choose an axis which makes things easy. So what I understand here, I have taken x-axis along the direction of field. So I have drawn a sphere, O is center. I have chosen x-axis to be along the direction of field. So how is the field? If at all I have to draw field lines will be along x-axis and equally spaced. It's a uniform field. That's how the field is. So if this is how the field is, if I take this sphere, which point will the field be maximum? In the direction of field, potential decreases. Opposite of field, potential increases. So maximum negative distance from P. This is the point where field will be, sorry, this is the point where potential will be maximum. This is the maximum potential point on the sphere. So basically, field is as we go along x direction. Field is x direction, potential is decreasing in x direction. So potential will be maximum where x is minimum. V max will occur. So important point is what? Where will maximum, sorry, first point I will notice here, potential decreases with x. Because field is along x. Hence, and V max on a sphere. Where would any point V sphere, where will maximum sphere will occur? It will occur at a point where x is minimum. Which is x minimum. This is the point where x is minimum. Here is the maximum potential. And similarly, this is the point which will have minimum potential. So this point potential is minimum potential 589. And this point potential is 589.8. So what I understand, over a distance of 2r, potential has changed by 0.8. That's a potential gradient. So as I move from here, in a distance r, potential changes by 0.8. And so if I have to draw equipotential surface, this is the equipotential surface. This is 589.8. This is 589. If I draw one more surface here, this will be middle of the two. So this potential equipotential surface at this will be equal to 589.4. If I'm interested, I have plenty of time. I can draw two more in between. This will be equal to 589.6, and in between, and this distance will be r by 2. This will be equal to 589.2. Now, this is how the potential equipotential surfaces are. What we need to do, we need to find potential at a point on the sphere. So whenever I have to find potential, all I need is x coordinate. So we understand here potential changes only in x direction. So the moment I have x coordinate, I can find the potential. Okay, and in terms of, so we need to find potential at a point where radius vector makes angle of 60 degree with the direction of field. So radius vector, let me draw a radius vector. Which point? Radius vector making an angle of 60 degree. So this is a point I need to find the field. And this point x coordinate is r by 2. And so this way, I hope all of you understand. So this point is x coordinate is r by 2. So from here to here, potential will drop by how much? In distance r, it drops by 0.4. It will drop by 0.2. So that's the potential here. So potential at that point will be 489.2. Had they mentioned what is the potential at a point which makes 120 degree with the direction of field, this would have been the potential. Any point I can calculate. All I need is x coordinate. So we know if we have to write a potential. So basically, okay, I can easily do that. Right. Next question. This also is understanding of field and potential form a uniformly charged sphere. So pay attention. This also is an important variation. One is okay, uniformly charged solid sphere has a potential V0 with respect to infinity on its surface. So when we talk about uniformly charged sphere, two things we need to be very, very clear. If I mark the distance r here, how does field vary as a function of r? This we have done in gravity. So field at the center is 0. So if I have to draw variation of field as a function of r from the center of a sphere, this is how the variation, this from here to here, linear variation. It will increase linearly. So whatever field is in the surface, and from here it varies as 1 by r square. From here, it becomes equal to proportional to 1 by r square. That's how the field varies here. And when we come to potential, what is potential important property? At any point, field is equal to, so the point was, that's, I think I'll just pay attention here. What is E equal to? The slope of Vx curve. Negative value of the slope has to be equal to field, right? That's what we need to understand here. So if field is positive, the slope has to be negative. Potential also, the slope has to be negative. This slope has to be negative. So how do we draw the field here? See, what we notice here, the slope, as I start from here, field is less. So Vx slope will be lesser here. As I keep moving in this direction, slope will keep getting more steep. So steepness of VR curve will increase because E is increasing. So what is the shape here? If I draw my VR curve here, if I take as a positive charge, potential also is positive. So VR curve shape will be something like this. Slope will keep increasing. And near to this point, slope is 0. So this is something starting from 0 slope. This is the shape of VR curve. Okay, and we know it is function of 1 by proportion to 1 by r. What is important? What is the potential? How the potential vary from here to here? From here, what I notice is still E is positive. Hence, slope will continue to remain negative. But as E value is gradually decreasing to 0, by the time the potential I reach here, the potential also at this point, the slope should become 0. The shape of VR curve becomes something like this. So VR curve, which point is the slope maximum? This point, the slope is maximum. Everywhere slope is negative. This is the reason because everywhere field is positive. And at the center, so whatever value of V we get here, it increases at a decreasing rate and final rate of increase becomes 0. And this is equal to 3 by 2 V. The potential at the center is 3 by 2 times the potential at the surface. Okay, so that's what we know here. This is how the potential varies. And now let's look at the question. This is a question again, 2015 question. Potential of the surface is V naught. So which point will the potential be? See, basically potential surface V naught. Where would the surface potential be equal to 1 point times V naught? There's only one point where the potential is 1 point time potential at the surface, which is at the center. This, of course, has to have at the center here. This is greater than V naught. V naught greater than potential greater than V naught can occur only within the sphere. So this point also, where would it lie? It will lie between 0 to R. We don't know exact value, but it will lie between 0 to R. This potential is less than V naught. So this point will lie outside. And now here potential is inversely proportional to distance. So since the potential is 3/4 of potential at the surface, the distance also will be 4/3 times radius. This potential will occur at what distance? It will occur at 4R/3. And this potential will occur at R is equal to 4R. And this is R is equal to 0. I hope all of you understood. So this is how we can understand. So moment we find anywhere outside, potential is lower than potential at the surface. Anywhere inside, potential is higher. And this is how it changes. If we have to find potential at R/2, in between region, how would we find potential in the interior region? Okay, interior region, since I know potential at R is equal to capital R, I will use delta V formula. Delta V from where to where? I will calculate potential difference between 2 points. Which point? R is equal to capital R and this point P at a distance R. So from here to here, work done. And we should know the field in between 2 points. Do we know the field here? Yes. Field as a function of R, ER is equal to field at the surface into a small y capital R. This is the field value into dr. I integrate from capital R to small r. I get the value of potential at a distance R. So if we have to do this case here, how would you have calculated V at R is equal to R/2 minus VR would have been equal to minus R to R/2. E/R into R dr, and then V at R is equal to R/2 is equal to VR. So what is potential at the surface? Potential at the surface, I write KQ/R, and then minus E/R, and it becomes R²/2. We substitute R and R/2. And we get the expression easily. So you understood here, this is something what we need to know. I integrated from where to where. Can I do this integration from infinity to R? We cannot. Why we cannot do infinity to R? This expression is valid only for then only, because afterwards it changes. So we can apply this expression only for region which is within the boundary of sphere, having uniform charge density. So there are 3-4 points here. I hope all of you paid attention to all the points here. All are understood. Okay. Okay, so anyway, I need a break. My throat is not okay. Luckily, it survived. I was not sure whether I can have full session.